Okay, excellent. And okay, the mic is all yours. Please, Professor Carter, we look forward to your talk about folding three-dimensional manifold.
Thank you very much, Sonia. And it's good to see many of you, albeit virtually, and sometimes just your um, tuxedo. So this is joint work with Sunmi and Bjori. And let's see. Okay. Obviously, I want to say happy birthday, Lou, and appreciate all the support that Lou has given me throughout my career. Most recently, he helped bring this book to fruition, which is joint work with Young-Ju and Bjori. It will not, nothing that I'm going to say today has much to do with Quipu, although by playing with these permutation groups, I started to get very interested in a lot of new things. And so some of them will touch on that. So I'm interested in either a cyclic or a dihedral branch cover. I was going to talk about alternating covers, but I don't have that much time. And of the M sphere. And M is going to be 2 or 3. And so we want the cover to be branched over a codimension 2 submanifold. So you can think of a knot, but if that's hurt your head, you can just think about a branch cover of a 2-sphere. And let's let D denote a disk of dimension 1 or 2. So it's either an interval or a rectangle. And a folding of M is going to be a map from M into SM cross D that satisfies the following conditions. So if you take away a neighborhood of the branch set, the map is going to be a generic immersion. And if you stick M into SM cross D, it might be singular, but if you project back down to SM, then you'll get the branch covering. And we'll say that the branch cover is folded. The yeah, so we know from Hilden and Montesinos that every 3-manifold is a 3-fold branch cover of the 3-sphere branched over a knot or a link. And this is just a reiteration. If I've folded the manifold into, say, the 3-manifold into S3 cross 0 n plus 1, there is a meaning in that n. Sometimes I can lift it to an embedding, and the meaning of the n is that the group that I'm going to look at has a permutation representation into Sn. And by lifting it, I'm basically lifting all my permutations to braids. Sometimes that can be done, sometimes it can't. We know of a case where it can't, but I'm not going to talk about that today. So the first example that I want to show you is something that Seiichi and I constructed a long, long time ago. And it's described as a sequence of braid charts that are interconnected by well-understood moves. And it will describe the 3-fold branch cover of the 3-sphere when it's branched over the trefoil knot. And the representation is just the 3-color representation that's inducing the branch cover. The 3-fold branch cover of the 3-sphere branched over the trefoil is in fact a 3-sphere. And the braid charts that we're going to see usually contain 4 black vertices. Some of the charts that we'll see have 1 or 2 white vertices, and a black vertex represents a simple branch point. So this is a picture that I lifted off the web of the graph of z goes to z squared, restricted to a disk, and then you see this double curve in the projection. The branch point is up here. So a way to construct such a thing is to take a light colored piece of paper, a dark colored piece of paper, slit the two down halfway down the seam, put the dark colored piece of paper behind the light colored piece of paper, tape the dark to the light, the left-hand side of the dark to the right-hand side of the light. And then imagine that the other sheet is passing in the fourth dimension um, below what we see in 3 dimensions. So this is a drawing of that, and this is another drawing of this. This sort of emphasizes the braid nature of the picture. Um, a white vertex in Seiichi's language corresponds to the braid relation. ABA is BAB. It also corresponds to a broken surface diagram of a triple point. Of course, the point is not a triple point in 4 space. It's a triple point when we project it into 3 space. We also have type 2 moves, and this is just a brief discussion of the things that can occur in charts. We have black vertices, crossings, and white vertices. These are the same things that Seiichi would draw, but I've chosen different conventions for drawing them. So the successive surface braids that we're going to see are going to differ by handle attachments or removals. They'll differ by surface isotopies, saddle moves, type 2 saddle moves. Some of the C3 moves that are moving a branch point through a transverse sheet, type 2 bubble moves, canceling or creating a pair of white vertices. Those are triple points. And I should have had a pause there, but I forgot to. So the handle attachment is indicated when we have parallel sheets. We go to this situation over here, and the removal is to cut those 2 branch points out. And this situation is obtained from our branch point picture by taking the appropriate copy of it and gluing them together to get this. And I know that most people, when they're thinking about a handle attachment, they think that the handle attachment should look like this. But we're going to have concentric spheres that are all going to have outward pointing normals. So we have to twist the handle before we attach it in order to keep the orientations consistent. And so we have this twisted handle. If you think about just turning a coin from head to tails, I know maybe you all still use coins. That's a piece of money that was common in the 20th century and earlier. So you just turn the coin over, and that's what that looks like. If you look at the picture on the left from the top and imagine it and have bad eyesight, then you're going to see the picture on the right. So that's why that's a handle attachment. There are 2 types of surface isotopies that we're going to have. We're going to have the endpoints of the handles slide past each other, and we're also going to bend the handles around like this. We'll have type 2 saddle moves. These are depicted here. We'll have the C3 move where we move a branch point through a transverse sheet. This is not the best picture of it. I thought it would be when I started to draw it, but I haven't redrawn it. But here you see I don't have a triple point, and when I push this branch point through, I do have a triple point. And so that's one of the C3 moves. We also have a pair of white vertices canceling, and we have a type 2 bubble move. Okay, so after the 2 one handles are attached and before they're removed, the surface that we're going to pay attention to is a pair of pants. And the pair of pants is actually embedded explicitly into a 4-dimensional product of this size here. It's going to usually take me about 15 stages to describe the movie. This width is 0 to 4, so there's some width on either side of the braid that's going to occur. And this thing, there are only going to be 6 braid generators there, 6 words in the braid group with six letters that are occurring there. And the last interval corresponds to where the handles are twisted. This is kind of funny, and I kind of like it because I don't think in topology we're supposed to talk about size, but when you start to draw these things, size does matter. So uh, the thing that we just looked at is actually training or a pair of pants. The boundary components are the three rectangles that we saw. And it's embedded in four-dimensional space as if one leg of the pants is turned inside out and the pants legs are twisted. So somebody looks at your cargo pants and twists and zips the left leg onto the right leg of the shorts and leaves them on the floor as if taking them off when they were sleepy. But the pants then are moving through four-dimensional space, and so they're actually running through a metaphorical four-dimensional dryer or washing machine if you're in a place that doesn't use heated dryers. Okay, so let me remind you that the birth of a circle represents an embedded disk. The birth of a sphere represents an embedded three ball. And similar things hold for DES. And so we're going to show this folding of this three sphere now. We have a moment of Zen where there's nothing, and a sphere is born. A sphere is born inside, and then the third sphere is born. And then we're going to concentrate on this temperate region in the three sphere. And you should think about these as meridional curves running around the spheres. But if you want to think about them literally as lines of latitude, then turn your head sideways. So this is the 0th page of our picture. We attach a handle here between the second and third sheet. We attach a handle here between the first and second sheet. And then we move these 2 points past each other, bend them around, move them past each other, bend them around, move them past each other. And if you were paying attention, you see that we just traced out a bit of the trefoil. But we want to complete the picture, we want to connect this branch point to this branch point and the 2 branch points on the left. But they're the wrong color and they're mired up in these other curves. So we can push this branch point through here. We can push that branch point through here. Now we'll just do a gentle isotopy, keeping the relative positions of the branch points, but moving the double curves out of the way. Then we can do 2 type 2 saddle moves, and then we can straighten those things out. That's an isotopy. Remove the handles. Then we have 2 branch points, 2 triple points. They can be removed, and then we can do 3 bubble moves. And then we're back to our original picture, and then let the sphere die, let the sphere die, and let the sphere die. Okay, so that's a picture of the three sphere as the threefold branch cover of the trefoil. If you don't like pictures, you can do it numerically. That's the same thing. And the whole thing is realized by a sequence of Kamada's braid charts. And so we have on page 1, we have the handle attached. We have a simple arc with 2 black vertices, another arc with 2 black vertices. You move one past the other, you turn them around, move one past the other, turn them around, move one past the other, and then move a C3 move, another C3 move, straighten them out, type 2 bubble move, etc. And that whole process, those sequence of braid charts, you can actually fit inside 3 space with the trefoil as the boundary. And the trefoil then appears as the branch set there. So the entire process, except for what's occurring on the yellow 2 spheres, lives inside this bit of 5-dimensional space. So you can go talk to your 5-dimensional carpenter and have them build that for you. And if you look at all the stills in the movie, there are 270 of them, and these are they. So there's the description of that branch covering. Um, as a retiree, I like to do things sort of inanely as much detail as I can. So the next example I want to show you is much more standard. We're going to look at the two-fold branch cover of the three-sphere that's branched over the torus knot T35, and we'll use the Seifert surface method to fold it into S3 cross 0, 3, cross minus 1 to 1. Starting point is emptiness. I hope that pause was long enough. Then a sphere is born. Then another sphere is born. And those two spheres, we look again in the temperate region, and we'll consider the Seifert surface for the 3-5 torus knot. With this is a gratuitous drawing of the usual Seifert surface uh, given the torus knot picture. I want to rearrange it so that it's in this position here. And these two crossings here occur in this region here. Ordinarily, I'd blow this picture up, but we're going to have the stills of that picture in just a moment. So we have these two parallel sheets. We attach a handle between the sheets. We attach another handle between the sheets, another handle between the sheets. Now I have a genus 2 surface, and then I'm going to repeat this process 5 times. We bend around, pass one past the other, do a type 2 saddle move, uh, bend that one up, bend that one up, and then do that on the bottom crossing as before. Do that 5 times and the repeat, and then remove the handle, remove the handle, remove the handle, and then you let the spheres die. So just it's worth giving a description of this process. And the process is that when the two spheres are born and the handles are attached between them, we have a genus 2 surface that's bounded by a handle body. The movie is a homeomorphism of that genus 2 surface. One can, if one is diligent, figure out what the Hegarde curves are, how the homeomorphism of the surface is acting, and then we have another solid handle body. So we've actually given a Hegarde splitting for this 3-manifold, and those of you in the know will know that I've just described the Poincare homology sphere. The threefold cyclic branch cover of the three-sphere branch along T25 follows a similar pattern. We start from emptiness. We have 3 spheres drawn nested, and then in the temperate region, we have this situation here. I do want to blow this up. So over here, we see this is analogous to the graph of z goes to z cubed. So that's those branch points that we have are no longer simple branch points. And then this is the process that goes through. So I won't describe these as handle attachments. They are handle attachments, but they're these nasty branch points there. And then we just slide one past the other, do type 2 saddle moves, type 2 saddle moves, straighten them out, and then repeat the process and then let those vanish. Okay, so the innermost sphere dies, the last sphere dies. Okay. This is the example that I really want to talk about. Although when I started this work, I was really interested in the Poincare homology sphere. And I'll come back to the Poincare homology sphere in a little while, but I won't show you the entire picture because I haven't drawn it yet. But I want to look at the torus knot T25, and I want to look at the dihedral cover of that. And I'll remind you that these are the constituents of a braid chart. If we have a braid, we can project it to a permutation. And in the braid chart, that's tantamount to just removing the orientations on the edges of the chart. And I want to look at the dihedral group, and I will want to look at it with this presentation, but I want to choose the reflection to be the reflection through the second axis. So it'll be 1, 3, 4, 5. And 1, 3 then can be written as 1, 2, 2, 3, 1, 2, and then 4, 5. And for some reason, I don't understand and I don't remember why I did this, and I'm mad at myself for doing it. I want X to be a clockwise rotation. Um, uh, After I realized I was doing the wrong thing, I had too many pictures drawn to change that. So um, these are the relations in the dihedral group. If you think about them, they're actually dual to the disks in the classifying space for the group. So there is a pentagon that's mapped into the classifying space. There's this quadrilateral that's mapped into the classifying space. And I also have this vertex where r squared is equal to 1 mapped in. That's not usually how things are done, but I like to do it that way. Now, later on, I'm just going to draw lines, and the lines are going to be colored either blue, pink, purple, or red. And the line that's thinner and blue represents the crossing between the first and second sheet. 2 represents the crossing between the second and third sheet, etc. And then my reflection, if I take the reflection times I, it's going to look like this, where we have this triangular tube, and then we have this crossing. And then my rotation is going to look like this. The negative rotation is going to be going in the opposite direction. And I just want to remind you that I can lift things to braids just by calling this thing -3 and then putting that in as a broken surface diagram. Okay, so the branch point that I'm really interested in that corresponds to the reflection really does look like this. But I can't compute with that. So I'm going to perturb that picture and write it as simple branch points. In the pictures that I'm drawing, I'm going to write everything in terms of simple branch points, but I could have used this vertex as well. Maybe I should redraw the pictures. Maybe I will. Maybe I won't. Okay. So for example, if I want to look at the dihedral cover of S2 that has 2 branch points and it's associated with the homomorphism of the annulus that maps everything to the reflection, then I would get this chart for it, and that would correspond to this movie. Okay, so we have a type 2 birth, we have a branch, 2 branch points are added, 2 branch points are subtracted, and then we have a type 2 death. There are 5 concentric 2 spheres that are involved. Sphere number 1 and 3 have been joined, and so have spheres 4 and 5. As I said, if I wanted to look at the 5-fold cyclic branch cover of the 3 sphere branched along the trefoil, I would use this picture, and the process would look very similar to the 2 previous examples where I showed you the Poincare homology sphere. Okay, this is the Fox coloring the torus knot T25, and I'm going to color the top arcs 2 and 3. The point is that all the other reflections are conjugate of a fixed reflection, and those turn out to be the most convenient ones to use. Okay, so I'm going to draw what's going to happen in the permutation chart first as a dihedral chart, which is a little bit strange idea, but it works. So we put a reflection in over here. Then we put a second reflection in. We move the points past each other. So we've passed the first crossing from the top down. Turn around, move them past each other. Turn around, move them past each other. Turn around, move them past each other. And then I guess I have to do that 5 times. And then I'm in this situation, and it's easier to work with if I write that rectilinearly. And I'd like to connect this branch point to this. I'd like to connect this branch point to the one in the upper left. And that way I would be passing the minimum of the diagram. But this chart is kind of messed up. What I can do is I can take the relations in the group and add a pair of them, and then add some more, uh, do some type 2, analogous to type 2 saddle moves, and keep moving that around until I get, oh, to here. This is a really good place to look. The green curves are the rotations, and I've got 5 rotations in a row here. And I think I got 5 rotations in a row over here. And so I can just insert a canceling pair of those relations. And then this branch point can be connected here. This branch point can be connected here. So we'll do those connections. And then after we remove them, we get to this picture here. And if you're a homotopy theorist, what you would say is, look, this last diagram represents a map from the two-sphere into the classifying space of the dihedral group. It's no homotopy because the classifying space is not supposed to have any two-dimensional homology or homotopy. But we're also interested in that null homotopy in the permutation representation. And so the changes between the dihedral charts that we used were, we introduced a relation and its mirror image as a canceling pair. There's a, oh, I misspelled monoidal. Okay, there's a monoidal category in which the objects are words in the free group on 2 generators, and the morphisms are generated by the relators, and as well as the trivial relators, such as x times x inverse is equal to 1. So the generating morphisms are all invertible. So that's this categorical statement of what's going on. In this classifying space, it has to do with homotoping disks past each other. So in that category, if you have 2 different words in the free group and they represent different elements in the dihedral group, the Hom set between them is empty. If they're the same word in the dihedral group, then there's a morphism between them, which is given by the diagram determined by the relations there. Okay, so these are some of the identities among morphisms in that category. These are some of the relations that we would impose upon the morphisms. Namely, everything is self-invertible. And then these are just have to do with trivial homotopies in the classifying space. But all those relations are consequences of the corresponding relations in the permutation group. And in the permutation group, the corresponding relations are given here. These are, this is a Roseman move. This is a Roseman move. These are versions of movie moves. And this is a Roseman move, and this is a Roseman move, at least in the projection. And since we're only in S5, I don't have to put a cubical relation for those things there. Okay, so yeah. So I'd like to be able to say that this relationship holds in the dihedral charts. And the proof of that is, well, I want to show that this surface, it's actually like 5 disks that are intertwined, is the same as these 5 disks that are intertwined. And there is a proof that requires just staring at this picture, and that is the picture is symmetric. And so all of the relations in the permutation group are invertible. And so there we go. But if you want to see the proof step by step, then you add some crossings, you add canceling pairs of triple points, then you add another canceling pair of triple points, you add some more crossings, add a canceling, more canceling pairs of triple points. Keep going like that until you get down to the last picture, and the last picture has 1, 2, 3, 4, 1, 2, 3, 4, which is x inverse squared. And the corollary is that this relation holds. And the reason that the corollary holds is that you can do type 2 saddle moves inside there. Similarly, you can see the relation that Rx inverse is the same thing, that the relation Rx inverse is XR inverse is invertible, follows from this sequence of diagrams here. Again, we have some disks that are intertwined, and you can move those disks, keeping the boundary fixed. Okay, so as before, a sphere is born, and we have 5 concentric spheres. We're going to focus on the temperate zone in there, and then we're going to attach some handles between them. So this corresponds to the reflection 2. This corresponds to the reflection 3. It may be difficult to see it at this scale, but that's the reflection 2, and it's conjugated by the rotation x. They move past each other, they bend around, they move past each other, they bend around, they move past each other, they bend around, etc. And I've counted that picture many times, and I think we have 5 crossings. If we don't, I've made a terrible mistake. Okay, so this is just an artistic rendering of the same thing. And here I'm going to draw some vertical lines so that we can see that the branch points don't move in the process. At least this slide is transverse to the 2-5 torus knot, and we're at the bottom of the knot. We're not going to move the branch points except up and down along those vertical lines. So we add the relation for R inverse X is XR inverse. And then it turns out that in this region, somewhere up here, we can do some type 2 saddle moves. So we'll do those. We'll move those, move the minima around, and then we'll put in some more relations similar to XR is our RX inverse. And we just keep looking at the diagram and seeing how we can simplify it until we get to this stage here. I had to push this up because I wanted to get some cancellation over here. And just keep going. I don't want to really describe the process here, but oh, yeah, I guess I want to describe the process at this stage. We have these 2 branch points are connected to this. These 2 branch points are pretty close to being connected to this. There's just a little bit that has to be cleaned up. And then we clean that little bit up. And so I can get rid of these 2 branch points. Okay, now I have 5 spheres sitting inside 3 space. They're all gnarled up. And if you think about the classifying space, then you know you can get rid of them. But I like to see how they get rid of them. So I'm going to straighten that thing out, and I'm going to move it around for a little while. And each of these moves is just a consequence of the projection of the Roseman moves. I have the scenario for a quadruple point, and it occurred in the wild, so I can perform that quadruple point move. That allows me to simplify some more stuff, keep simplifying it. And then I have another quadruple point in the wild, and I can simplify it or do the quadruple point move. And that allows some more stuff to be simplified. And all of a sudden I get nested circles, and those can be undone by type 2 bubble moves. And the 5 spheres die successively as in the previous case. Okay, shift gears for a while. Suppose you look at the dihedral group where n is an odd integer, and then this is the presentation. Then all the reflections are conjugate by means of x to a fixed reflection. And in general, I'd like to choose the reflection to be the one that doesn't make diagrams too messy. And it turns out that this is the reflection I want. And it can be written like this. So the last two letters switch, and then these switch, and so forth. And then in the diagram where the branch points haven't been desingularized, this is what a branch cover of the two sphere with two branch points looks like, corresponding to the representation that sends the generator to R4. There's something I forgot to tell you about the dihedral cover of S3 branched along the 2,5 torus knot, and that was that all of the, after the handles were attached, the whole thing was a two-dimensional sphere. And you can just compute the genus of what's going on. So that dihedral cover is also a three-dimensional sphere. Okay, so, right. The next slide shows, in general, if I have a dihedral cover of a knot, of S3 branched along a knot, then I just can think about the dihedral cover as the 2b minus a situation. So I put this reflection, I conjugate by a copies of x, and then this thing's going to be conjugated by b copies of x, and this last thing's going to be conjugated by c copies of x. And so we get 2b minus a is equal to c. But we know that these, I can switch the r and the x just by using the invertibility of that relator. And in general, I can prove the invertibility of the relator in the permutation representation. It's going to get nasty. And at any rate, after that's done, you see, since C has to be equal to 2b minus a, then I can add in this relation, and that allows me to get the two ends of the reflection together. And so this is what's happening at the under arc of the knot. Yeah. Okay, so that's pretty much all I have to say. But I also want to thank Lou for giving us the marvelous toys that he's given us. One of the toys, of course, is the bracket. And in my strange way of thinking, I like to think about the bracket as corresponding to a Mobius band sitting in 4 space as part of a cross cap. And I guess I want to go back and say one more thing. Yeah, right. The line spacing in this picture, the lines are 2 centimeters apart. And the entire picture is roughly 2 meters by 1.5 meters. That's a big picture. I don't think I could draw it any smaller than that. I'm not willing to put the lines at a centimeter apart. Um, and in that movie that I showed of the thing, I skipped a lot of steps by using the lemmas. So that's a really big immersion of the or folding of the three sphere into five space. And that's all I have to say. Okay.